Hello Year 11. So for the last of our revision videos, getting you all ready for the exam on Friday, which is physics, which for most of you will be your last exam, which is wonderful. So let's make sure that we really smash this one. We're going to ace it. We're going to do so well. So what do you need to know for the Physics 2 paper? And if you look in the description, there should be something about the Physics 2 paper, link to the paper, link to the mark scheme. So have a go with that one. So what do you need to know about? We need to know about forces. And one of the things you need to know about is the difference between scalar and vector. Now this is really easy because vector is committing crimes with direction and magnitude. Oh yeah, I'm not doing the movement. So that's how you remember it, literally. What's vector? Direction and magnitude. Magnitude is just size. Scalar only has one of them, and that is size. So size for scalar, and vector has size and direction. The difference between speed and velocity. Speed is scalar because you've just got size. 10 meters per second, 30 miles an hour, whatever. Whereas a vector would have a direction with that. You travel at 30 miles an hour east. Okay, so you've got that little bit more information. You also need to know the difference between contact and non-contact forces. And this includes things like gravity, which happen, and magnetism, which are non-contact. They happen even if you're not touching them, and other things like friction and air resistance and upthrust and things like that, which all require you to touch them before it will have an effect. So we are going to try a question on vector and scalar, and that is question 4.1. So we're only going to do 4.1. Let's have a look at it. Here we go, lovely question. Difference between vector and scalar. Pause the video and write it down. Off you go. All right, let's go through the answers. Vector has, of course, direction and magnitude. Scalar, magnitude only. Okay, so what I'm doing now is I'm doing a workout. I'm lifting up my lovely little axolotl and putting him back down to where he started. So the question is, how much work have I done? And the answer is none. Well, thanks physics, I'm not going to get fit like this, am I? The reason being that work is force multiplied by displacement. Now, loads of people go, oh yeah, it's force by distance. So if you've lifted up your axolotl, 1/2 metre, or whatever it is, then put it down by 1/2 metre, then you've done 1 metre, and then you need to multiply that by the force used. So your distance is 1 metre. My force, I don't know, what are you? Should we say 5 newtons? Yeah. So then I would multiply 1 by 5 and say I have done 5 Newton meters of work. But no, it's displacement. Because my axolotl started off back where he began, I have done no work. So just remember that one. It is a bit of a nasty trick. It's the overall displacement, not the distance. You need to know about elasticity. And thankfully, you are always given this equation. This isn't even one that they think about not giving you. So you need to know about elastic potential. You need to know that the spring constant is proportional to, not the same as, proportional to the force until you reach the elastic limit, and then it'll either go little bit, rumph, or little bit, stop moving. You need to know about speed, which in physics we always measure in meters per second. So you do your meters divided by your seconds. Make sure you do know all your triangles and you can rearrange equations. The equations are given to you, and thankfully lots of them are in the units so you can figure them out. But if you can't, it's given to you, okay? You need to know about acceleration, which is meters per second squared, or meters per second. And the reason for this is it's the change in speed over time. Speed is meters per second and time is seconds, so it's meters per second squared. In physics, we tend to say the change in velocity over time, just because you can accelerate by turning a corner and not changing your speed because you've changed your direction at that point. That's a bit of a nasty one that they might come out with. And distance time graphs. Oh, these are beautiful. With a distance time graph, when you are going up, you are moving away from your start point. So if you've got your axes like this, moving up, you're moving away from your start point. You move up at a really high steep angle, or steep gradient rather, then you're going to go fast. If you're moving at a shallower gradient, then you're going slower. If you are stationary, it is a flat line on the graph, and going downwards means that you are returning to where you came from. So we've got going up, being stationary, so you're just going straight across, and then coming back to where you began, so you're going down. Okay? Oh, we're doing such a good workout today. No, we're not. Physics has said no. Yeah, speed time graphs. The distance is the area under the graph, and the overall distance is how much under the graph it is. So if you're doing, say, 30 miles an hour, 30 meters per second for 10 seconds, then your area underneath, you should have 30 at the top for 30 meters a second, 10 seconds along the bottom. 30 times 10 is 300. You can use a calculator, don't worry. And the higher the gradient, the faster you are going. Higher the gradient, you're accelerating, the faster you're accelerating. And a stationary line, if it's along the x-axis, you are still. A stationary line anywhere higher up means you're travelling at a steady speed. You need to know about Newton's 3 laws. Okay, and I've done videos on Newton's 3 laws before that you're very welcome to go and watch. And of course, the second law, forces, mass times acceleration, is given to you in the exam, so you don't even have to remember it. So of course, law 1 is every action has an equal and opposite reaction, and law 3 is an object in motion will tend to stay in motion unless acted on by another force. You need to know about stopping distances, and there are 2 things you need to know for stopping distances. One is when you stop, you need to think as well. So you've got your thinking distance and your braking distance. Your thinking distance is always going to be about 2 seconds. That's why when you drive, you have the 2-second rule. And then the actual braking distance depends on several things, such as the condition of the tyre, the condition of the roads, how fast you're going, obviously. Your thinking distance depends just on you. So that's going to be, have you had caffeine? That might make your reaction time shorter. Have you been drinking alcohol? That may make your reaction time slower, and that's why we don't drink and drive. And you also need to know about momentum as well. Okay? And obviously be able to do all the sums for these. The other thing you need to know is about waves and magnets. I'm going to do magnets first, and then we're going to do an exam question. So magnets. There are 3 magnetic elements that you need to know about: iron, nickel, and cobalt. And those are the 3 magnetic elements. If you put a magnet to a magnetic element, so say I have a magnet and my little axolotl here is made out of iron, I've got a magnet and whoomph, it's attached. I turn my magnet over and whoomph, it's attracted. Okay, non-contact. My magnet didn't have to touch my axolotl for it to be attracted. If on the other hand you have 2 magnets, like poles repel. Okay, they don't want to go together, but different poles are going to attract. So how could I tell if my axolotl was made out of iron or made out of a magnet? I've got a magnet here, it's attracted, so it could be iron or a magnet. I turn my magnet over. If my axolotl is a magnet, it's going to be repelled. If it's iron, it's still going to be attracted. And then you have other metals such as copper and aluminium, which are not attracted to a magnet at all. And in fact, that is what question 1 is on. So if you turn to question 1, we can go through it. Here we go. I have got 5 different metal samples: iron, steel, aluminium, copper and tin. A student placed a magnet close to each metal sample. Describe what happened. Off you go. So what's going to happen? The iron and steel are magnetic because steel is mostly iron, so they'll be attracted. The other 3, nothing will happen. There we go. And that's what they want you to say. Okay, so the other thing about magnetism you need to know is the right-hand rule and the left-hand rule. Right-hand rule is nice and easy. You just put your thumb up like this. Okay, this is the direction of the current, and this is the direction of the magnetic field. So you just line up your thumb with the current, and it will tell you where the magnetic field is. The left-hand rule, okay, they've all got to be at 90 degrees to each other. And it looks like this, okay? And it looks like you're in a gang in the middle of the exam when you're doing this. It's really cool. So your thumb goes straight up. F for thumb and F for force. B, I'm pointing straight at you now. So B is for the magnetic field, because it just is. They just assigned a random letter to it, which is great. And then I is at 90 degrees to the other 2. So that is now pointing over there, okay? And I is for current. I is always for current. It's because it was originally called induction in French, okay? And of course it was the French who were developing this. So FBI, nice, easy to remember. Force, magnetic field, current. And you line up 2 of them, and then that means you can tell the other 3. Sorry, you line up 2 of them, and then you can tell the other 1. Okay, just got waves, and then I'm going to do a couple of calculation questions with you. Waves, we all know the wonderful song about waves, and we can put them all in order. We know it's radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays, and I'm so proud of myself for getting through that without singing. You need to know what all the waves are and what they do. You need to know that the shorter wavelength means the higher frequency, and these high frequency, short wavelength ones, these are the ones that cause problems. These are the dangerous gamma rays. These are the X-rays to see broken bones and hidden bombs. These are the UV light as well that comes from the sun. And all these can mutate DNA. UV light less so. And gamma rays kind of useful for killing cells and radiotherapy, but it can also mutate them. Which is why, if you have radiotherapy, they keep checking up to make sure that they haven't caused cancer as well as killing it in later years. You need to know visible light, we use it to see with, and fibre optic cables and stuff like that. But yeah, seeing, that's the main thing. And you need to know red, orange, yellow, green, indigo, violet, so blue, indigo, violet. There's actually only 6 colours. But interesting bit of history, Isaac Newton, who did this, was super religious, and he was into his religious numerology, which if you know much about Christianity, you would know that if you actually read the Bible, that's a bit of a no-no. But anyway, Isaac Newton was really big into this, and 6 apparently is the number of sin, and 7 is the number of God. And as a rainbow is God's promise to never flood the world again, it couldn't be 6 colours, it has to be 7. And that's why we've got blue and indigo, and not just blue and purple. Yeah, so that little bit of knowledge aside, you've got the 7 colours, and you need to know that they will split up when they go through a prism. And the shortest one is going to be refracted the most. So you get red, which is the longest one, is just because of the length of the wave, it'll be moved the least. So with your rainbows, you get red on the top, and the one that's bent the furthest will be the violet. Red is of course next to infrared, which is used for heating things up, and for remote controls. You need to know microwaves, cooking things and communications, including with phones, and radio waves, communications, satellites, things like that. We actually do get radio waves from the sun, but they can't get into our atmosphere, so we can't decode them and see if there's any information in there. There probably isn't, because we have to code our radio waves, but wouldn't it be exciting if there was? Right, I think that's about it. I'm going to go through a couple more questions with you now, but that's all the knowledge you need. Let's put it into some practice now. And the thing that I forgot about waves, which is why the video's jumped a little bit, the bit that I forgot to tell you was that you also need to be able to do wave speed calculations, which are really easy. You need to remember that waves are measured in meters, and that's from one crest or peak to another peak or crest, or from one trough to the other trough. Don't measure it in the middle, because then you need to measure one whole wavelength, which is an up and a down, and if you just measure half of it, which is to the next point where it touches the middle, then you'll get all your sums wrong. You also need to know the amplitude is how far it moves from the middle. So a wave with no energy is flat, and then as soon as it starts to move, so this is the baseline, it'll start to move up and down around that baseline, and so the amplitude is how far it's gone, how much energy it has, and that's just half of it. And the wave speed is the wave speed is the wavelength in meters, and that's multiplied by the waves per second. You've already got it divided as the per second, so your frequency in hertz is waves per second, and that's why wave speed isn't meters divided by seconds, it's meters times frequency, because your frequency is already in per seconds. Yeah, does that make sense? Okay, let's try a few questions. We're going to start with a 6-marker question 2. Here we go. We've got height of the ramp affecting the acceleration of a trolley down the ramp. Here is some of the equipment used. How are we going to figure this one out? Well, first of all, don't panic if you get something like this and you just say, I don't know. You can always tell me your variables. An easy variable to do, hang on a second, would be the height. You've got some wooden blocks here. I could change the number of wooden blocks. Excellent. So my independent variable is going to be my height, as determined by the number of wooden blocks. And I can measure that in centimetres as well, that's fine. What's my dependent variable going to be? Well, it's about acceleration. So, I don't know, maybe I'm measuring time. Time seems like a good thing I'm going to measure. And then control variables, and that's easy. Same trolley, same ramp, same person doing the timing, because then you're going to have the same reflexes, all that sort of stuff. Right, so now we've got a start. We've got our variables, and we'll always get marks for saying variables. So what am I going to do? Well, I'm probably going to start off with a ramp that's 1 block high and put my trolley on the top, and then time how long it takes to go down the ramp. And I'm going to do it 3 times. Doing it 3 times is always good, because then I can find anomalies. So always repeat experiments. Then I'm going to do 2 blocks and take it down again and do that 3 times and calculate a mean average, ignoring any anomalies. And then I'm going to do 3 blocks. Right, sorted. But it wants to know about acceleration. Right. How am I going to do that? Well, acceleration is in meters per second squared. So if I know the length of my ramp, say that's 1 meter, because I want to make my life easy on myself. So I'm going to do 1 divided by the time in seconds squared, and that should give me my acceleration. Just remember as you're doing it, if you start with the back wheel of the trolley right at the end there, you have to stop timing when the back wheel of the trolley is right on the end there. Otherwise, it's not 1 metre, it's 1 metre less the length of the trolley. Okay, I do have the mark scheme, so let's see if my ramblings would have gotten me 6 marks. Here we go. Place a wooden block under the ramp, vary the heights with different numbers of wooden blocks. Excellent. Measure the height of the ramp. Excellent. Measure the distance travelled. Brilliant.
Measure the time taken using light gates. I didn't say that. I said have a person doing the timing. Light gates would obviously make it a lot better. Release the trolley from the same position each time. I had that. Release the trolley without applying a force. I didn't say that. I said let go of the trolley. But I suppose you do need to say you're not applying a force, you're not pushing it. Otherwise, the examiner doesn't know that you know that. So I am losing a few marks here. Repeat at the same height and calculate a mean. Yay! Repeat for different heights. Yay! I got that one. Calculate acceleration using one of these ones. So, actually, I did that. Distance divided by time. V is, no, that's end speed minus start speed divided by time. Or V squared minus U squared over 2S. These equations are given to you. So you can just say, this is how I would measure the acceleration. That would work. I'm fairly sure mine would work as well, but this is the one they want you to use. Okay, how many would I have gotten? I might have gotten 4 or 5. I didn't say quite everything, and I didn't use a data logger or a computer, which you would have done for the required practical. Okay. Let's have a go at another sort of accelerate-y question. So we're going to use this sum because I know that everyone hates this sum. And let's try 6.3. So here we go. We've got a car being driven at a constant speed past a speed camera. Oh, thank goodness. Constant speed. I don't have to think about acceleration. Oh, but wait. The camera recorded 2 images of the car 0.7 seconds apart. The car travelled 14 metres between the 2 images being taken. The maximum deceleration of the car is 6.25 metres per second. Calculate the minimum braking distance for the car at the speed it passed the speed camera. It's another 6 marker. So the first thing we're going to have to do is calculate the speed the car's going at, the average speed. So that's 14 metres, 0.7 seconds. Speed is metres per second, so 14 divided by 0.7. So that's the first sum I'm going to do. And then I need to figure out the minimum braking distance, not stopping distance. We're not having to include thinking time, just braking distance. So here we go. Here comes the answer. Make sure you've paused it and had a go yourself using A equals V squared minus U squared divided by 2S, where A is acceleration, V squared is your final speed, U squared is your initial speed, which is your 14 divided by 0.7, and 2S is 2 multiplied by the distance. You have to rearrange it. So we have got, here we go. So we started off by calculating our speed at 20 metres per second. As we are going to stop, our end speed is going to be 0. So V squared minus U squared is 0 squared minus 20 squared, which is equal to 2AS, which is 2 times minus 6.25 times S. So we've got minus 20 squared times 2 times 6.05. Remember, the negative means it's deceleration. And you plug all that into a calculator. Don't do it in your head. Minus 400, which is minus 20 squared, divided by 12.5 should give you 32 metres. So it would take 32 metres for that car to stop after the thinking time. It's quite a nice one, actually. Once you know what you're doing, you just need to think about what you need to calculate. And usually one of these 6 markers needs you to do 2 sums. So for this one, before I could calculate my minimum braking distance, I had to calculate my initial speed. So they will give you a 2-step calculation. So make sure that you are using 2 equations in a 5 or 6 marker, unless it's a really easy one, but a lot of them need you to use more than 1 equation to figure it out. Okay, let's move on. And let's have a go at 4.3 and 4.4. I mentioned you needed to know momentum earlier. I didn't go through it because we've got an exam question on it. I want to see how much you can do on your own for this one. What links mass, momentum and velocity? You can look that one up. It's going to be on your equation sheet. And it is, of course, momentum is mass times by velocity, or P equals mv. Please notice this one is a P. The bowling ball has a velocity of 5 meters per second when it hits the pin. The momentum of the bowling ball is 26 kilogram meters per second. I really love it when the units tell you what to do. My units are literally telling me it's mass times velocity. Calculate the mass of the bowling ball. It's only worth 3 marks. It's straightforward. Pause the video and you have a go. And the answer is... my M is equal to 26 divided by 5, which gives me 5.2 kilograms. If you don't put your answer in this little bit here, so long as it's a bit obvious what you're doing here, and I've not put in the divide symbol there, so it's not as obvious, you've still got 5.2 kilograms. You can still get the marks, but just to be on the safe side, pop it in the bottom here as well. Okay, that's all from me. Best of luck for Friday's exam. Keep practicing, keep doing the equations, do the past papers, and good luck for Friday, for the future. Go and enjoy.